everyone, for our 11th entry in the CSRI Summer Seminar Series. I want to remind everyone that these talks are recorded. Today we have with us Dr. Irina Tazauer, who is currently a DMTS in the Quantitative Modeling and Analysis Department at Sandia National Laboratories. Irina is located in the Livermore campus, and today she's going to be giving us an overview of the CLDERA Grand Challenge. So with that, I'll let you take it away. Looking forward to it.
Thanks a lot, Darby, for the invitation and for the introduction. It's a pleasure to be one of the speakers in this year's CCR seminar series. So as Darby said, this talk is going to be a bit of an overview of the CLDERA Grand Challenge LDRD project, whose goal is to develop a novel foundational approach for attributing climate impacts. So in terms of my role in the project, I am one of the thrust leads under CLDERA, along with Lindsay Shand and Laura Swiler. And just to acknowledge kind of the rest of the CLDERA leadership team, the PI is Diana Bull, the deputy PI is Kara Peterson, and our project managers are Andy Salinger and Ben Cook. And we have a rather large interdisciplinary team of, I think, around 45 or so staff members as well, and so you'll see their names throughout the presentation, and I'll acknowledge all the names kind of at the end of the talk. So let me kind of get started here. So the outline of the talk is as follows. So I'll start with a little bit of motivation for CLDERA. I'll then describe CLDERA, so I'll talk about kind of what are its goals. I'll talk about connections to Sandia mission spaces. And then I'll also define what is a Grand Challenge LDRD project in case folks aren't familiar with that. I'm going to talk a little bit about our exemplar that's driving the research under CLDERA, which is the 1991 eruption of Mount Pinatubo in the Philippines, and more broadly what's called stratospheric aerosol injection, or SAI. I'll talk about simulating Mount Pinatubo using the DOE climate model called E3SM. I'll do a few kind of deep dives into each of the three thrusts under CLDERA, which are shown in this picture here on the right. There's simulated pathways, observed pathways, and attribution. And then I'll end by talking a little bit about V&V and showing kind of a fun movie we generated very recently using some of the simulations done under CLDERA. So let's start with motivation. So I think, you know, many of you are aware climate change is a growing national and global security concern. And when you're looking at kind of climate change, there actually are kind of a number of things that can serve as sources for climate change. So this includes non-persistent natural forcings, policy choices, and recently what's known as climate interventions or geoengineering. And so, you know, for those who aren't familiar with geoengineering, this is basically kind of exactly what it sounds like it is. It's the deliberate manipulation of the Earth system to try to counteract the effects of climate change. And at the bottom of the slide is a timely example of an actual climate intervention that's already kind of in progress. And this was actually, I saw this on CNN just last week. Just by coincidence. And so the example is China's Sky River project. And so this started some years back. This was launched unilaterally by China. Basically, they installed, you know, tens of thousands of fuel burning chambers across the Tibetan mountains. And what they do is they produce silver iodide particles that seed moisture clouds. And the goal of that is to try to control rainfall over the Tibetan plateau. And so, you know, why does Sandia care about climate change and geoengineering? Well, you know, federal agencies, DHS, DOD, DOS, DOE have articulated an interest in risk assessments of climate impacts from not only natural climate change events, but also climate interventions. As the effects of climate change compound, it's becoming more and more important to be able to distinguish the impacts of an intervention, anthropogenic climate change, and natural variability in the climate. And moreover, you know, what it's looking like is that decisions are soon going to need to be made on policy, legislation, treaties, and national security posture. And so as an FFRDC and a national security lab, Sandia really wants to be kind of on the forefront in terms of having scientifically kind of valid technologies to help inform some of these decisions. And so in terms of kind of where, you know, things are currently in terms of being able to distinguish the impacts from these different sources of climate change and informing decisions. Unfortunately, confident scientific attribution of a source like Sky River and the climate to some physical impact is at best onerous and at worst impossible today. And so, just taking this Sky River example again, if if India has a drought, let's say, and they believe that it's partially caused by Sky River, there aren't tools right now that would allow you to actually determine to what extent that may actually be the case. Okay. And so I'm going to be using this term throughout the talk. I've already used it twice, attribution. So I just wanted to define that just so that we all kind of know what I'm talking about. So attribution is the process of evaluating the relative contributions of multiple causal factors to a change or an impact. So we're trying to figure out what was the source associated with an impact in the climate. And usually we're interested in some assignment of statistical confidence when we're trying to do attribution. And attribution in climate is very, very challenging. And so listed here are some of the reasons why this is hard. So the first reason is we tend to have a high internal variability in the Earth system that can obscure the connective relationships between sources and impacts. And so under CLDERA, using as an exemplar the 1991 eruption of Mount Pinatubo. And I'll talk about this in the next part of the talk. But this volcanic eruption is an example of what's more broadly defined as SAI, or stratospheric aerosol injection. And this is something that can happen both naturally through eruption of volcanoes or fires, for example. And it's also something that people are looking at as a climate intervention. And so the goal here is basically under this 3-year project, we're kind of focusing, developing and fine-tuning and validating our methods on Pinatubo, on this SAI exemplar, with the idea being that we would then apply our tools to study other exemplars and other climate impacts or climate or geoengineering strategies in follow-on work to CLDERA. So, research questions under CLDERA, so they're all focused around these pathways. So can we discover pathways in simulated observed data? Can pathways inform contributory rankings of sources to an impact? And can pathways cull or reduce the search space for your solution when you're trying to solve that attribution problem? And the hypothesis that we have is that if we're able to trace these pathways between sources and impacts, we can actually increase certainty in attribution. And so it's always useful when you're talking about a project to put it in the context of what is the current state of the art. And so this slide shows some of the approaches that are currently used to study climate attribution. So a few popular approaches include fingerprinting, structural causal modeling, and emergent constraints. And the best way to kind of describe these approaches is they're based on sort of a hunting and pecking, and that's why there's this chicken picture on the right if you're wondering. But the way that they work is you basically posit a source impact pair, and then statistical methods are applied to data to try to infer connective relationships between the posited source impact pair. And so there's several kind of downsides to this. So the relationships that are inferred are often linear. The relationships are, they tell you correlations, but not necessarily causations. And these don't actually uncover pathways, right? You're just kind of have to guess, two things that are connected, and the methods can check if that's actually true, but they're not actually discovering pathways. And there's a nice quote here from Peter Caldwell, who's a climate scientist at Lawrence Livermore, that connective relationships are often unbounded from ideological relationships, and you can get physically meaningless source impact correlations. And so under CLDERA, the goal is to move beyond a correlative approach. And so we are kind of starting with some of these methods, as you'll see in some of the thrusts and subthrusts in CLDERA, but we're extending these methods to take into account multivariate dependencies to encode pathway information. And then we're also bringing to the table methods that are currently intractable. So an example would be PD constrained optimization. And the goal is to move beyond this correlative approach and really establish connective and correlative, connective and causal relationships. So I mentioned, a couple slides back that CLDERA is a Grand Challenge LDRD. It occurred to me when I was putting this together that the interns may not know what that is. So I wanted to spend a little bit of time just talking about this. So I'll start with LDRD. So LDRD stands for Laboratory Directed Research and Development. And so this is a funding program at the national labs that focuses on high risk, high reward ideas that maybe need to be matured a little bit before they could be funded by more traditional funding sources. There's a quote here from the LDRD website: transformational research inspired by and enabling the mission. So LDRDs are really competitive. There's a call that comes out every year. There are a lot of different research foundations, mission foundations, and strategic initiatives you can apply for. And typically they're 1 to 3 year projects, usually in the 200 to 600K per year range. And so what is now a Grand Challenge LDRD? Well, in some sense, it's kind of like a very large LDRD, a super LDRD, an LDRD++. But it's actually a little bit more than that. So it's one of the strategic initiatives in the LDRD program, really, really competitive, more competitive than regular LDRD. The Grand Challenge LDRDs are 3 year projects with a maximum $5 million per year budget. And this is really a very, very large budget to effectively go to just Sandia. There are large, projects funded by DOE with a lot of different institutions and universities and labs that have budgets smaller than this. So this is really quite a bit of money. And the goal here is really to develop core differentiating capabilities in which Sandia really wants to establish a foothold, where these projects are also kind of aimed at making strides towards tackling what Sandia has recognized as grand challenge problems. Okay, so it's not just a very large project. And CLDERA is currently one of 4 Grand Challenge LDRDs that are at Sandia, and the first one ever that is focused on climate or more broadly geosciences, as it turns out. And Darby and Stefan asked me to talk a little bit about how this project connects to Sandia missions and strategies. And so CLDERA is aligned with Sandia's recently launched climate security strategy, whose goal is to advance the state of the art in several key climate capabilities. And so this picture is one that Rob Leland, the director of the recently created Climate Security Center 8900, likes to show. So the 4 capabilities are awareness, intervention, adaptation, and mitigation. And you can see CLDERA falling here under the intervention part, since the vision is that the tools we're developing the modeling and analysis tools we're developing will help us kind of study the impacts of climate modification or geoengineering type strategies. Okay, so that was kind of the background. So let's now talk about some of the actual science. And so the first thing I wanted to talk a little bit about is this exemplar that we're using, which, as I said before, is SAI, more specifically the 1991 eruption of Mount Pinatubo. And so this slide tells you a little bit about this eruption. So Pinatubo is located right here in the Philippines, about 15 degrees north of the equator. Mount Pinatubo erupted on June 15th, 1991. So these are some pictures here, before, during, after the eruption. It was the largest eruption of the satellite era, releasing 18 to 19 teragrams of sulfur dioxide gas into the atmosphere. A lot of this actually fell out very quickly as ice and ash and things like this. And so we were left with a 10 teragram net injection of SO2 gas into the stratosphere. And so this picture, this kind of notional schematic here on the right, it kind of shows you what were some of the immediate effects following the eruption. And so what happened is we had this SO2 gas be released. The SO2 gas was converted through different processes and chemical reactions to a variety of different aerosols. So H2SO4, H2O, other aerosols. And so you had this sort of, cloud of aerosols that formed here. And the most kind of, obvious impact that happened had to do with how these aerosols kind of started playing with the radiation. And so the impacts are kind of listed here on the left. Essentially, what these aerosols do is they scatter incoming long wave radiation from the sun. So that's what these squiggly lines are showing. What that does is that increases planetary albedo and cools the climate system, since you have less energy coming in. So that's kind of one effect. The other effect is that these aerosols actually absorb infrared shortwave radiation that's emitted from the surface. And so what that does is that actually kind of prevents that from leaving the atmosphere, and you end up with a warming of the stratosphere, which is this kind of upper part of the atmosphere. The lower one we refer to as the troposphere. So I'll be using those terms in the remainder of the talk. And so that was exactly kind of what was seen. So you had a 0.4 to 0.6 degrees Celsius global cooling that lasted through 1993. And you had a warming of the stratosphere up to 3 degrees Celsius as well following the eruption. And so what I just described is one example of a pathway for the Mount Pinatubo eruption. This is what we call kind of the temperature pathway, or aerosol direct effect pathway. So you had, emission, aerosol formation that changed what's called aerosol optical depth, which is how much direct sunlight is prevented from reaching the ground by aerosols. We had changes in radiative flux, like I described, and then we had these temperature changes, the warming of the stratosphere, cooling of the troposphere. And interestingly, while these two temperature effects are kind of well agreed upon, there was another temperature effect that's less agreed upon. And so this is the warming of the northern hemisphere, the first winter of the tropical eruption. So it's actually disputed if that was due to natural variability or due to the eruption. But the main kind of idea is we do have some notion of what these pathways look like for Pinatubo. So this is the notional diagram that shows you some pathways. So the one that I talked about is the aerosol direct effect, which is the solid red line here, leading to the air temperature changes. We also have more kind of sophisticated pathways that are maybe a little bit less certain. So an example would be the aerosol indirect effect, which is this non-solid red line. So in that one you have the eruption, you have sulfate aerosol production, you have aerosol sedimentation transporting aerosols from the stratosphere to the troposphere, which has the effect of modifying cloud optical properties that leads to increased cloud brightness, which can reflect sunlight and lead to cooling. Also, it's thought to have led to decreased precipitation. And we also have kind of more downstream impacts. So it was observed that there was a decrease in sea level that was due to lower sea surface temperature and a reduced ocean heat content following the eruption, and that led to thermal expansion of the oceans, leading to the global sea level decrease. And so, other impacts are listed here. So these impacts are very well kind of characterized. And so that's kind of one of the reasons why we pick Pinatubo as our exemplar. There's really a lot of observational data that can demonstrate the direct and indirect effects of the eruption for validating pathways and validating our methods. Some of the other reasons we pick this exemplar are listed here. So the source in this exemplar is external to climate feedbacks. The impacts are large enough to rise above the internal variability of the climate system. And importantly and interestingly, this natural event that I've been describing actually has a climate intervention analog. And so this picture is one that shows you kind of what are some geoengineering strategies people are looking at. So here's the cloud seeding that I talked about already. What people are actually looking at is this number one here on the left that's circled. So this is kind of SAI as a climate intervention. People are actually looking at building special planes that would inject aerosols kind of continuously into the stratosphere in order to achieve the same cooling that was achieved naturally by Mount Pinatubo. And so 1 teragram sulfur dioxide per year emitted in this way can produce about a 1 degree Celsius cooling, 0.1 degree Celsius cooling. And so before I continue, I just wanted to give a little bit of a disclaimer. So, this diagram is notional. So by showing this, I didn't mean to imply, in case it implied that pathways are actually known for Pinatubo. While the impacts of Pinatubo are well characterized, there actually have not been any publications that have demonstrated concrete pathways connecting more than 2 processes. So finding those pathways is a non-trivial task for this exemplar, even though we kind of have an idea of what some of the nodes on those pathways should be, if that makes sense. All right, so let's now talk about how we actually simulate our exemplar of Mount Pinatubo. And we're doing simulations under CLDERA using what's called E3SM, the Energy Exascale Earth System Model. And so for those who aren't familiar, E3SM is the US Department of Energy's system model or global climate model developed in collaboration with 8 national labs and 12 academic institutions. It has these 6 different components for different pieces of the climate system. So atmosphere, land, river, ocean, sea ice, and land ice. And the idea is that each of these parts are developed separately according to the relevant partial differential equations and relevant discretizations, and then they're put together in the E3SM using this flux coupler that basically passes things back and forth as source terms, boundary conditions, fluxes, and so on. And it does it in a way that ensures, stability, accuracy, and importantly, conservation, which is really critical for climate models. And so the E3SM is designed to run on DOE's advanced computing platforms and address energy relevant science questions, which are currently energy and water issues looking out about 40 years. And we're using under CLDERA version 2 of E3SM, which is the newest version of E3SM. It's not released yet, I believe, to the general public, but we do have access to this through a collaboration agreement with the E3SM. And so I want to talk a little bit about kind of the simulations we're doing and what in E3SM makes it a good choice for simulating Pinatubo, and some of the changes we had to make to E3SM to be able to do these simulations. And so I'd like to acknowledge Kara Peterson, who's the lead for the simulations. She's also the deputy PI. She's in 1442 down in New Mexico. And I'll just kind of preface this by saying that simulating SAI is extremely challenging for a lot of climate models and really an active area of research, and that's certainly true for E3SM as well. And so E3SM, when we started kind of working with this, it had a number of capabilities that are really important for SAI. So the atmosphere model includes the stratosphere. The top of atmosphere for E3SM goes up to 64 kilometers. Which is kind of well above where we'd like it to go. We usually discretize this with 72 vertical layers, and most of our simulations are running on a 1 degree resolution horizontal grid, which looks like this. The other kind of piece here is that E3SM includes key process models for things like clouds, ozone, and aerosols. And so the way to think of these process models is these are like subgrid scale parameterizations, or maybe turbulence models in CFD, if you're familiar with that, where basically these are really fine scale processes that we're just not going to be able to resolve in the model. So we have to introduce some kind of parameterization to capture those effects. And so specifically, we're using the club model, which has a turbulence closure for clouds, the MG2 cloud microphysics models, LINOS V2 linearized ozone photochemistry model, and the MAM4 aerosol model. And this model is particularly important. We've had to do some adjustments and tunings to this model to get things to work, as I'll show on the next slide. And one of the team members on CLDERA is actually the lead developer of MAM4, Professor Xiaohang Liu at Texas A&M. And so we've been working closely with him to try to make some of these modifications. Now, there was one key limitation to E3SM before we started this project, and that limitation is that there were no prognostic volcanic aerosols in the model. And so what that means is radiative forcing due to the aerosols from volcanic eruptions was prescribed. And so one of the early modifications we did was to actually make it possible to simulate with prognostic volcanic aerosols, so that you can capture these reactions, conversions of SO2 into H2SO4 and things like this. In the initial results we did with this, we found that we had the chemical reactions that were expected happening, but aerosols were sedimenting out too quickly from the atmosphere. And so to fix this, one of the things we looked at was improving the implementation of prognostic aerosols in E3SM V2. And this was done by effectively tuning this MAM4 aerosol model. And so, without getting into too much detail, but still telling you a little bit about how this is done, the MAM4 model basically has models for different modes or kind of particle sizes. That's what's shown here on the right. And what we had to do was basically change the properties for some of these modes or particle sizes to match stratospheric size distributions that we have from data. And by doing this, we were able to validate the model against both observational data as well as other climate models that have been shown to very accurately model SAI. And I'll talk a little bit about that at the very end when I show the movie that I'll kind of end the presentation with. And so another big task in simulating Pinatubo is actually understanding what isn't captured in E3SM. The objective of CLDERA is not to develop E3SM. We're just putting in kind of the minimal things we need to be able to do this as well as we can. And so, you know, it could be that certain processes or certain nodes on that notional diagram that I showed are missing in the E3SM. And so we'd like to know that so that we're not looking for those when we go and validate some of our tools. And so what we've been doing for this is we've been working with Professor Christiane Jabłonowski at the University of Michigan to try to assess the realism of E3SM stratospheric circulation, and also to evaluate the model's ability to capture processes like quasi-biennial oscillation or QBO, Brewer-Dobson circulation, and so on. And this can be done in kind of a really neat way by kind of dropping tracers into the model and kind of following them around and looking at how they trace out some of these processes. So this table shows our simulation plan for CLDERA, and the details of this are not kind of super important, although you can see, you know, we have runs with Pinatubo, without Pinatubo as kind of control simulation, sensitivity studies planned. I'll talk about the sensitivity studies later. The main thing I wanted to call your attention to is just the computational budget. So our runs are planning to take about 34 million CPU hours, and this is really very, very large, okay? And we're doing these runs on both Sandia HPC, so the Skybridge machine, Boca, which is a condo cluster, as well as the Cori machine at NERSC. And just to kind of make you a little bit appreciate the planning involved here, you know, one of the challenges is that we, you know, even though some of these simulations we're not doing until, you know, years 2 and 3 of the project, we actually have to, in the first year, before we start any runs, we have to already know, you know, which quantities we want to write out when we do these simulations and how often we want to write those out. Because if it turns out that in year 3, we need we need a quantity written out from our simulations to do some analysis that we start doing. If we haven't done that, we're not going to be able to start over and rerun everything to dump that quantity to be able to use it. And so really a lot of careful project planning is required to be able to execute these simulations and in a way to allow us to achieve the project goals. Okay, so let's see how my time. Oh, good. Okay, so the next section of the talk is going to talk about the 3 CLDERA thrusts. So these three kind of circles here, overlapping circles. Just a little bit of a caveat. You know, this is going to be a relatively high level, so you know, the goal is to just give you a flavor of the methods we're using and developing, and hopefully, you know, people with different backgrounds can find something that they, you know, that's related to things they're interested in or working on. I'm happy to talk offline if anyone is interested in more details, or certainly I could point you to some of the folks who are developing those methods, so you could reach out to them for those details. And so the first thrust is the simulated pathways thrust, and this is the thrust that I'm leading. So this part is going to be a little bit more detailed just because it's sort of near and dear to my heart. And the goal here is to find impacts from a source. So basically to discover these source impact pathways using simulations and simulation data. So before I talk about the research composition, I wanted to come back to this question of what is a simulated pathway, just so that kind of everyone is on the same page on the definition. So earlier I gave this heuristic definition that a pathway is the chain of physical processes from a source to its impacts and their evolution in space and time. I also gave examples of pathways, so you know, these direct, indirect, downstream impacts on this notional Pinatubo diagram. The way to think of a pathway is in terms of sort of, you know, mathematics, is you can think of it as a time-dependent directed acyclic graph, or DAG, that represents the dynamics of a physical system. So this is an example of one of these DAGs. The QI here are the impacts or the quantities of interest, or, you know, the nodes on your pathway graph. And you can see this is evolving in time, and an edge from Qi to Qj at time t means that Qj is impacted by Qi at time t. And you can see that you can get kind of new nodes appear and new edges appear, and edges change and so on. So this is one way to think about the graphs, and you'll see actually some graphical representation of these in the coming slides as well. So in terms of simulated pathways, we're trying to identify and rank pathways. We're pursuing this goal by using 3 complementary research subthrusts that fuse Sandia's strengths in data analytics, computational modeling, and E3SM, or more broadly climate science. So the 3 subthrusts are statistical methods, computational monitoring, and anomaly detection. I'll talk about them on the next slides. This picture just shows you kind of how things are kind of how these subthrusts are interacting with each other and interacting with the simulations that I talked about already, where, we're using a lot of the data from the simulations. Methods developed in one subthrust will feed into the others, same with kind of data. And by being able to identify pathways using different approaches, we're, hoping to kind of have that workflow help with the validation process by providing confidence in some of these approaches, if we're able to some of the pathways, if we're able to discover them using different approaches. So I'll kind of go into each of the subthrusts under simulated pathways. The first one is statistical methods, and there's actually 2 different approaches we're looking at. The first approach is random forest regression, or RFR. And so for those who aren't familiar with RFR, this is a data-driven technique for determining feature importance and finding associations in data sets. It does this by using groups of decision trees that you train on available data. And what we're doing here is not using RFR the way it's usually used, which is for prediction, but to use feature importances from random forest to identify weighted pathways from one variable or feature to another. And so the inputs here are time series of various features or variables of interest. They can be either simulated or observed. The data will be on kind of some raw grid here. What we do is we group or cluster the data into G groups. We train a random forest regression on each group. We calculate feature importances for each group. And then based on those feature importances, we can create this pathway graph. And the thicker edges here are edges that have larger feature importances. So these are kind of stronger pathways. And so by generating this graph and querying this graph, we can see what kinds of pathways exist between different features and what are their relevant strengths. The second task under statistical methods is sensitivity analyses. And so on their own, these won't really give you pathways. The goal is more to generate data for some of the approaches that can find pathways, like random forest regression and anomaly detection, and also to generate data for the attribution thrust that I'll talk about a little bit later on. Also, a goal of this is to determine robustness of pathways to changes in both SAI and model-related inputs. So that sort of thing is important for understanding how much our approaches will transfer over to other exemplars potentially. And so we have 2 kinds of sensitivity studies that we're looking at. The first one will vary eruption elements like the mass, timing, height, and location of Pinatubo. So looking at how Mount Pinatubo could have been, how low can you go, or how small can the eruption be to still be detectable. And then the second study is more of a traditional sensitivity analysis that varies model parameters. So we're looking at varying MAM4 aerosol and MG2 cloud microphysics parameters to see how sensitive the pathways are to those parameters. Here we're hoping to do a global sensitivity analysis if we can afford it, and we are looking at some lower resolution configurations of the model, like these top 2 shown here, to try to kind of maximize how many ensembles we can possibly generate. The second subthrust under simulated pathways is computational monitoring. So kind of as it maybe sounds, the goal here is to do analyses kind of in situ while running the E3SM. The first task is profiling. What we're doing under profiling is we've instrumented E3SM to communicate with a lightweight library that we've written called CLDERA tools that performs kind of in situ operations and analyses while running E3SM. So the way that this works is we first generate a baseline by doing a control run with no Pinatubo. We also generate what we call a base DAG, which is a directed acyclic graph that just encodes the different dependencies between different variables and routines in E3SM and processes. So these two things kind of tell E3SM what to track. And then when we do a run with Pinatubo, CLDERA tools perform statistical analysis by comparing QOIs inside the code with the baseline and tracking the propagation of anomalies in real time to generate one of these time evolving pathway DAGs, like the one you see here. And this is an actual one that was generated where you can see some of these, chemical reactions like the conversion of SO2 to H2SO4, SO4, and so on. And then the second task under computational monitoring is tracing. Atmosphere models typically contain a variety of tracers of kind of different flavors. The goal here is to add tracers to enable analyses both for evaluating E3SM and for identifying source impact pathways. The first kind of tracer we've been adding is a passive tracer, which passive tracers are tracers that don't feed back into the atmosphere but can track source evolution. And so, as I said earlier, Professor Jablonowski from Michigan is using these tracers to evaluate climatological dynamics and changes to those dynamics to try to understand what processes are and aren't captured in E3SM. And something kind of new that we're doing is trying to use these tracers to infer pathways and pathway changes. And one idea to do this is by detecting tracer flow patterns and their evolution using what's called Lagrangian coherent structures, or LCS. And so what these are basically surface trajectories that exponentially attract or repel tracers. They're often used to study things like atmospheric rivers in the atmosphere. This is a nice movie that Everett Wenzel generated for me. Oops, I wonder why it's not playing. Oh, there it goes. So what this is showing, you an example of one of these Lagrangian coherent structures. Specifically, I'll just play this again. It's showing advective transport of massless Lagrangian particles in a CFD code, and as time advances, the passive scalar quantity that's shown here, it evolves from an initially simple distribution to a rather complicated structure characterized by large gradients, and that structure is the dominant Lagrangian coherent structure. And it's fairly straightforward to identify that by kind of dropping in these tracers and computing the number density of Lagrangian particles within the simulation. And then the other kind of tracer is active tracers. These tracers feed back into the atmosphere through physics processes, and these allow us to track relative contributions along nodes in a pathway. And really, these let us kind of reduce the number of simulations we have to do, because we are able to look at kind of what happens with and without Pinatubo in a single simulation, rather than doing kind of separate with and without runs. The last subthrust is anomaly detection, and this is a little bit of a misnomer. This is really kind of anomaly detection, combined with clustering. What we're doing here is leveraging some tools developed under a project called iSmile, which stands for Institute Machine Learning for Intelligent Data Capture on Exascale Platforms. This is led by Warren Davis, one of our team members. And in this iSmile methodology, the way that kind of you identify anomalies is you break up your grid into partitions, and you calculate what are called signatures, which are compressed representations of the data in each partition. And so what we're doing here is we're still doing this step, the calculation, the breaking up into partitions and calculation of signatures. Once we have the signatures, rather than looking for anomalies, we cluster the signatures. That's what these different colors are showing. And the idea is to take these clusters and to trace them in space and time, to actually trace out some of these graphs that represent the source impact pathways that we're seeking. Okay, so that was simulated pathways. Let's now go to the next next thrust, which is observed pathways. This is led by Lindsay Shand, who's a statistician in 5573. And so again, before I get into the research composition, I just wanted to define an observed pathway. This definition is a little bit different from simulated pathways. The way to interpret observed pathways is as relationships or correlations between dependent climate processes. rather than finding pathways that have not been postulating. The goal here is to validate proposed pathways and quantify changes in the relationship between pathway nodes. And what's being done is statistical methods and statistical models are being developed that can account for the dynamic evolution of aerosols over space and time, that can handle multiple complementary sources of data, and can also take into account uncertainty in some of the observations. And so I wanted to also just mention briefly the types of observations that are available. So this table summarizes some of the data that we have for observations from 8 different instruments, mostly satellites. And you can see in the rightmost column the type of data that we have. So SO2 mass, aerosol optical depth, plume height, stratospheric temperature anomalies, and so on. And in addition to the observational data, we also have what's called reanalysis data. And reanalysis data is basically a blend of observations with past short range weather and climate forecasts, where your observational data is going to have holes in it, kind of like this image here shows. And so the idea is to fill in those holes using data assimilation techniques to kind of bring in some of this observational data to get a more complete picture of the past weather and climate than you would get with just observations alone. And so we're using 2 different kinds of reanalysis products, ERA5 and MERA2, which I'll mention in the next slides. So let's now talk about the research composition. So again, 3 subthrusts that I'll focus on. The first one being change point detection. Change points are different than anomalies in the sense that they're defined as significant persistent shifts in the underlying mean or variance of a process, with the keyword being persistent. So it's not just an outlier that kind of forms at one time step and maybe goes away later on. The goal of change point detection is to inform pathways by finding changes and shifts in climate processes towards accounting them in some of the statistical models that are being developed that I'll talk about in the next 2 slides. 2 different kinds of methods are being looked at: space-time change point detection methods. This is work with Professor Bo Lee at University of Illinois Urbana-Champaign. These methods can detect when and where climate shifts have occurred with respect to a source, which is important for doing some of these analyses and achieving this goal. The other type of method is elastic functional warping methods. And these use some pretty sophisticated mathematics, the concept of diffeomorphisms and elastic distance, to try to isolate both amplitude and phase shifts in the climate that are not due to expected weather patterns. And shown here are some preliminary results applied to this ERA5 reanalysis data I mentioned on the previous slide, where both a phase shift and an amplitude change point were identified in 1991. And this is consistent with the Pinatubo eruption that happened in that year. The next subthrust is space-time statistical methods. So here we're trying to quantify the spatiotemporal evolution of aerosols and climate impacts by developing dynamic spatiotemporal models. And so these models are intuitive and interpretable ways to represent complex dependent physical processes that can change both in space and time simultaneously. So the models take the form shown here. And so what's encoded here is you have in these kind of first terms here, those are kind of baseline trends. So things like seasonal effects. You also have noise and spatial variability that's accounted through this epsilon t, eta t, and wt. And then the theta t term in this last expression allows you to take into account temporally varying spatial distributions of dynamic parameters. And one of the new things that's being looked at is quantifying pathways using a multivariate covariance matrix. And one of these lines in the formulation, where by making this multivariate, we can model the relationship between variables while quantifying their dependencies, which can be important when you have a lot of kind of impacts that are working together in a synchronous way. The last subthrust is hybrid statistical and deep learning methods. So here we're trying to understand trends in observational data using interpretable and explainable methods, and to test if data supports postulated pathways. The main workhorse here is echostate networks, which use reservoir computing to efficiently estimate what are called recurrent neural networks, or RNNs, for capturing short-term and long-term spatiotemporal dependence. So this is kind of the whole formulation here. for the echo state network, where the RNN is this last two stages, the output and the hidden stage. All the terms here are learned from data. One of the new things we're doing is adding this spatiotemporal residual delta T, which accounts for some of the regional spatial trends that aren't captured by just kind of the raw variables like temperature or aerosol optical depth, and this can make the model more explainable. And another approach we're looking at to make these models more explainable is the incorporation of permutation feature importance, or PFI, which can determine which variables at which times are important for forecasting. So last but not least is attribution, and I'm going to try to kind of wrap this up so there's a little bit of time for Q&A. This is led by Loris Weiler in 1400. Now we're turning our attention to kind of the inverse problem, so trying to actually find the source given the impacts. And again, three subthrusts. So I'll kind of quickly go through these. So subthrust 1 is enhanced fingerprinting. This is something we're working on with Professor Kate Marvel at Columbia, who's really an expert in fingerprinting for climate science analyses. So for those who aren't familiar, a fingerprint is a spatial and or temporal pattern that highlights an impact. Mathematically, this is the first principal component obtained from doing an SVD on a data matrix. And fingerprints can allow you to do both detection as well as attribution, where detection is the process of demonstrating that the climate has changed in some defined statistical sense without necessarily providing a reason for that change. And so for detection, we take our signal, we project it back onto the EOF, we check if it goes beyond a 2 standard deviation limit. And for attribution, we basically check the magnitude of the fingerprint in a regression formulation and look at its signal to noise ratio to see if this is high, and if it's high enough, then we can actually say that we've attributed the source to the impact. And so the pictures on the right are showing preliminary results where we did both detection and attribution of Pinatubo using traditional fingerprints. What's new under CLDERA is what we call enhanced fingerprinting. And so that's basically extending fingerprinting to work with multivariate fingerprints, to use multiple variables along a pathway in the fingerprint, and also to allow you to study short-term SAI events with regional impacts. Typically in fingerprinting, you need very long time period data, and you're looking at decadal changes. And so we're trying to make it possible to do analyses that are more short-term. The second subthrust is what I kind of have been talking about throughout the presentation, kind of the main goal of the project, which is solving the inverse optimization. So formulating and solving a large scale PD constraint inverse problem to find some source parameters data, which could be magnitude, height, and location of your eruption in our case, that minimizes the difference between simulated and observed aerosol concentrations constrained by our atmospheric PDEs. One of the new things that we're doing with this is replacing these PDEs, which are embedded within the E3SM and really not accessible, but replacing these with deep operator neural networks, or DONs, learned from simulation data from the E3SM. And so by doing this, we basically take this problem out of E3SM, and that opens the door for doing things like PD constraint optimization without having to intrude into the E3SM code, which would be very, very challenging. The other new thing is to add pathways to this formulation. I don't have it written mathematically, but you could add them either as constraints or as penalty terms in the objective function. And so what we've been working on for this is actually developing and prototyping a workflow to do this inverse optimization. So that's been for a synthetic case called the Gaussian plume plus model, which is given by an advection diffusion reaction problem. So you have this 2D domain, here's the PDE, and you have a source that's in this lower left-hand corner, and basically the you'll see this concentration spread throughout the domain and advect and diffuse and so on. And so the workflow, the goal is to estimate SO2, the SO2 source given downstream concentration measurements. The way that the workflow that we developed works is we first do a PCA to create a reduced operator. We then use TensorFlow to approximate the operator using a neural network trained on time-step pairs. And then once we have the neural network, we substitute the equations with the neural network, and we do a an optimization using the rapid optimization library from Trilinos. And this has really helped us. Prototyping this on this workflow on this example has really helped us fine tune and refine some of these methods and kind of understand how they work. The last thing here is causal modeling. So, causal modeling basically takes large-scale time series data and discovers a causal network represented by a graph like this one. So it's similar to the pathway graph. The goal is to establish relationships between a set of variables to discover or confirm causal relationships. And in addition to the structural causal modeling approaches that are commonly used, we're also looking at causal network learning approaches like PCMCI, where we're fitting a graphical model of covariance by iterative conditional independence tests to generate this causal network. And on the right are some preliminary results that have shown from an early prognostic simulation that we get all kind of these causal dependencies that we expect, such as SO2 being converted to H2SO4, SO2 changing aerosol optical depth properties, and so on. So I'm kind of running out of time here, but I should be able to wrap up pretty quickly. One of the last things I wanted to talk about is verification and validation. And so really a key part of CLDERA is what we call a tiered verification approach, where in the first half of the project, so the first year and a half or so, we're developing, refining, and fine-tuning our methods in the context of synthetic and idealized formulations. And this also gives us some time to generate simulation data of the actual eruption. And so the synthetic formulations are basically ODEs with encoded dependencies that we can define, and we could also add noise to them. The idealized test cases include that Gaussian plume plus model, and this is how the solution looks like if you're interested, and also a problem called HSW++, which is Held Swarthville Williamson. This is a traditional test case for Earth system models. It's run using E3SM. It uses realistic Earth circulation in the atmosphere in the E3SM, but it has idealized forcings, topography, and chemistry. So that this was, let me wait for this to start over, but you can actually inject a source like Pinatubo and watch it spin around using those processes. So there it goes. But we're able to control things here and control pathways so that we can make sure that we're able to represent the pathways that are encoded within this idealized case. And, obviously we want to get to verifying, validating things on Pinatubo. And as I kind of alluded to earlier, we're looking for pathways that have as nodes the majority of the known aerosol direct, indirect, and downstream impacts from Pinatubo. And careful assessments of what isn't captured in E3SM is really critical for doing this validation. And so I wanted to end with a little bit of eye candy here. And so I already showed this result on the right. I didn't say a whole lot about it, but this is the simulation that goes with it. And so what this is showing is on the left is the default E3SM v2, and on the right is CLDERA E3SM, which is our version of it with the tunings and the other additions that I mentioned. This is showing the stratospheric sulfate burden, which is the total mass over some area. Essentially, that's what the burden is defined as. And the main kind of point here is that the result on the right is actually a lot more physically consistent with what actually happened, and you can see a lot more aerosols going into the northern hemisphere, which isn't seen in the default simulation. And in fact, as I mentioned earlier, if you compare it to observational data into other models with the CLDERA E3SM, you get remarkably good agreement, which is not the case for the base model. And so let me wrap up. So I talked about CLDERA. The goal of CLDERA is a beginning to end attribution workflow to study attribution on the climate system. We're prototyping methods on Pinatubo and SAI with the goal of then expanding the methods to other climate impacts in subsequent work. And I'll just end by acknowledging the CLDERA team. So these are all the staff members that have contributed to this presentation on the project. I have pictures of our leadership team, and I'll stop here. Thank you for your attention. I'm sorry I went a little bit longer than I expected. I guess we did start a little late, so maybe it's not so bad. Happy to take questions.
Awesome, thank you so much. We do have a couple questions in the chat. So Sandra asks, if your various different analysis methods do not converge to the same pathway, what is the proposed methodology to establish the true etiology of a process. Which method would you trust more? What criteria determines how closely they need to converge to accept as an established pathway?
Yeah, that's a good question. So I think, okay, I think that we're looking for pathways that have as nodes. So let me go back to the slide. Kind of some of these known direct, indirect, and downstream impacts. It could be that there are, so these are just some nodes that we have. Some of these nodes are potentially kind of disputed. So these are, again, kind of a notional diagram. I think that one thing that would be interesting if we're able to obtain different pathways would be to try the different pathways in the inverse problem and to see if they give you different results, and to see how that inverse problem behaves with those pathways. So I think, if we're able to get a more get a more correct result with one of the pathways, I think that would be potentially one reason to say which one that one pathway is correct. But I think that there can be potentially different pathways, and I think it will be interesting to study how different pathways affect the inversion workflow. I mean, certainly if we get a pathway that has impacts on it that are just completely non-physical for Pinatubo, then that would be a reason to kind of discount that pathway. But there could be multiple pathways that are kind of reasonable, certainly.
Hemant asks, do you impose bounds on the time horizon for establishing etiology? Chaotic systems are notoriously difficult to reason about causality over long time horizons.
Yeah, these are all really good questions. So in this particular case, I had it on the slide, but I didn't say it because I was trying to not take too much time. We're looking at 3 to 5 year runs. So starting a little bit before Pinatubo. So they're pretty short horizon in this case. Certainly, if you're looking at other impacts, or if you're looking at SAI as a climate intervention, it is a little bit different, because you may do that for a longer period of time, or you would do that for a longer period of time, and you would be injecting things kind of evenly distributed rather than a point source injection. And so I agree that it will be interesting to try to see sort of what are the limitations of these methods, given the chaotic nature of the system when we are trying to do longer term attribution. I don't really see it being a huge issue, because we are looking at relatively short term in the grand scheme of things for now. But certainly that's something that I think we'll have to think about as we look at other impacts in the future.
Excellent. We have one more question from anyone online. I invite them to unmute. I'll ask it a softball. At the very beginning, you were showing us some geoengineering diagrams, and you had mentioned that some aerosol injection would cause a 0.1 decrease in temperature. Is there any indication over how long that effect before it would become apparent? Would it take like 6 months before that starts happening, or would it be more delayed than that?
That's also a good question. I don't remember, quite honestly, that this was from a reference. I don't remember the time scales of this. You do need to do the injection continuously. But I can certainly find that and get back to you. I think you would have to do it continuously for some period of time, but I don't remember what the time is. In terms of Pinatubo, when you have the point source, it's actually, so in that case, if the eruption, you'll have the most impact if the eruption, if the SAI, the point SAI happens in the tropics, as it turns out. And in terms of how quickly it goes around the equator, it's on the order of months. And then it takes longer for it to get to the poles, and you could actually see that in that simulation I showed at the end. But yeah, I don't know off the top of my head the answer to your question, but I imagine it would be on the order of at least months for this, and I can send you the answer offline. This is from a paper, so they probably mentioned it in there.
Still very, very cool. Well, thank you so much. Let's thank our speaker again. Irina, this was fantastic. I really, really enjoyed this talk, and I can't wait to see more of the CLDERA Grand Challenge reports start coming out. I'll be sure to keep my eye on it.
Great. Well, yeah, thanks for having me, and feel free to shoot me an email if you'd like to talk more or have more questions.
Absolutely. I may just.
Okay.
A lot of stochastic calculus questions that popped in my brain.
Oh, but, right.
Either way, thank you again, and thank our audience. I would like to just say that next week is our final talk in the CSRI Seminar Series, and we'll have with us Megan Dahlhauser and Kenny Rudinger, who will be speaking about quantum benchmarking and quantum EMV. So